The 2026 Nature measurement recorded a hydrogen transition frequency of 730,690,248 610.79 kHz. This yields a proton charge radius of 0.8406 femtometers. This dimension aligns with the muonic hydrogen value, providing a test of the standard model at the 0.7 parts per trillion level. This result brings the decade-old proton radius discrepancy into agreement beyond 5 standard deviations. This measurement represents a bound-state QED transition frequency. It is mathematically distinct from a direct geometric photograph of a rigid boundary. In this context, the proton charge radius operates as a parameter for finite-size correction within the spectroscopic equations. A charge radius defines the effective second moment of an electromagnetic distribution. Within the tetrahedral token framework, the radius constitutes a rendered space projection of electromagnetic support. Attempting to define a geometrical diameter by counting configuration space cells leads to mathematical contradictions. The underlying topology and the rendered radius occupy different tiers of the theory. Advanced control over Stark shifts and line shape asymmetries allows us to isolate this projection from systematic distortion. The 0.8406 femtometer value quantifies the interface between proton structure and spectroscopy. It defines the observed support width within a specific readout channel. This standard continuum integral treats the charge radius as a smooth radial distribution. This standard integration assumes a completely continuous background, which is fundamentally incompatible with a purely discrete tetrahedral topology. The tetrasphere model replaces that integral with a discrete sum across the lattice support. The denominator represents the total time-average electromagnetic weight of the proton eigenmode. The numerator links the mapped position of each node to its localized weight. The term WP of V denotes the time-averaged occupancy of a specific lattice support point. The projection map pi translates configuration space support into a position in rendered space. This synthesis maps the discrete eigenmode through an electromagnetic filter to produce a continuous charge density. The measured radius is a derivative of this density map after the projection is complete. Topological closure and measured radius remain distinct entities. A stable ontic loop can project a broad or narrow charge support depending on the dynamics of the channel. To explain the compact radius, we look at the configuration space mechanics of the proton eigenmode. The proton is a color singlet composite formed by 2 up quarks and 1 down quark. Up quarks have twist index 1, down quarks have twist index 2. The resulting composite twist of 4 represents parity-balanced closure with minimal stall. This triangular loop achieves stability through shared transport paths, which remove redundant inversion steps on the lattice. The wedge cycle protocol dictates a local update budget, limiting the complexity of the transport paths. The term I gamma represents the total inversion stall burden along the loop's geodesic. Minimizing this stall burden forces the occupancy weight into a more concentrated spatial configuration. Peripheral states that require high inversion costs are dynamically suppressed, carrying less time-averaged weight. The precise 0.8406 femtometer measured radius describes the specific, highly concentrated charge support kernel produced by this low-stall closure mode. In the experiment, atoms are prepared in the metastable 2s state using a 243 nanometer laser. There is a 6 order of magnitude difference between this 243 nanometer scale and the subnuclear femtometer scale. They are dimensionally distinct. The 243 nanometer value serves as a spectral addressing scale for state preparation, not a direct measure of proton size. However, the number 243 corresponds to 3 to the 5th power. This aligns with the theory's base addressing manifold of 3 to the 9th. That base manifold of 19,683 fixes the defect density used to calculate the coupling correction. The theory introduces a refinement layer to increase spectroscopic capacity. This layer uses a multiplier of 3 to the 5th, or 243. Multiplying the base defect density by this refinement factor produces a lifted manifold for complex spectroscopic readout. Applying an orbit repair protocol to this lift preserves the directional coherence of the system. This numerical alignment suggests that the experimental addressing wavelength targets the specific refinement tier used by the model to handle spectroscopic data. The actual experiment's addressing layer corresponds exactly to the 3 to the 5th refinement index established by the theory's internal hierarchy. Discrepancies in the proton radius often stem from treating 3 distinct physical tiers as one concept. Tier 1 is ontic closure, the discrete topological arrangement of the proton eigenmode. Tier 2 is rendered charge support, the continuous density cloud detected by electromagnetic probes. Tier 3 is the spectroscopic address, the external wavelength used to interrogate the atom. This structure explains the difference between muonic and ordinary hydrogen measurements. The heavier muon orbits closer to the nucleus, sampling the deeper, more concentrated sections of the rendered support layer. Refined systematic controls in ordinary hydrogen experiments eventually allowed for the resolution of this same core depth. The 0.8406 femtometer radius is the expected value for a stable, low-stall closure. Ultimately, this new precision measurement confirms the highly compact projection of the underlying tetrahedral loop into continuous space.